See this one extra hop.
Hey, so we are doing homework number 10, problem number 1. Poisson process is defined by the following properties. The number n t1 t2 of the points ti in the interval t1 t2 of length t equal to t2 minus t1 is a Poisson random variable with parameter lambda t. And this is the numerical expression. It's a Poisson process. We've seen that in homework number 4 or 3 from chapter 4, and also in our midterm. The second corollary is if the intervals t1, t2, and t3, t4 are non-overlapping, then the random variables nt1, t2, and nt3, t4 are independent. And the third corollary is that at a time moment t, there is no more one Poisson point. Using the points ti, we form the stochastic process x of t equal to n of 0, t. And to homework to part A, we're trying to find the expected value of x of t. We start off with the Poisson. You'll see I use this. I'm going to find e of x of t, the expected value of x of t, and also the expected value of x squared of t, which I'll show you. It's a little cut off right here, right there. Pause the video if you need to, definitely. So here's my work. I took the derivative with regards to lambda of both sides. E of lambda t stays e of lambda t. This side turns into k times the quantity of lambda t to the k minus 1 over k factorial. And then this, you separate out both. You have k over, so k to negative 1 right here. K over lambda t times quantity of k, lambda t to the k over k factorial. And then, so you have your 1 over t over here. You move that over here, and then you move e to lambda t back over here. You get k times e to the negative lambda t times the quantity of lambda t to the k over k factorial, and that equals to lambda t, and that is the expected value of x of t. So we're going to start from the same point over here. Here's our Poisson. We take derivative again as we do here, except over here we take the derivative one more time to result in e to the lambda t equaling to the sum of from k equal to 0 to infinity, k times k minus times the quantity k minus 1 times lambda t to the k minus 2 over k factorial. You split them up, and over here you see that you split them up first, and then you move e to the lambda t over to this side, which makes it for both parts of the this side of the equation 1 over e to the lambda t, which equals to e to the negative lambda t. This quantity of lambda t squared moves up. This is technically lambda t to negative 2, so this becomes lambda t squared, or the quantity of lambda times t squared. And this equals to the summation from 0 to infinity, k squared e to negative lambda t, some quantity of lambda t to the k over k factorial, minus the summation of from k equals 0 to infinity, k to the e to negative lambda t, times the quantity lambda t to the k over k factorial. And we know this part equals to lambda t because we did it over here. So we move it to the other side. Lambda t, the quantity of lambda t squared minus lambda t equals to this this part right here, as I've showed here. Now this part is equal to the expected value of x squared of t, and therefore expected value of x squared of t equals to the quantity of lambda t squared minus lambda t. And we'll use that in the second part of the problem. In the second part of the problem, we are asked to find the autocorrelation of r t1 t2, which equals to expected value of x t1 x t of 2, and we start off with the condition first that t2 is greater than t1, because that is what we are taught. We'll see that, using t1 and t2 are mainly qualitative. The 1 and 2 are mainly qualitative aspects, and we and we also must know that x of t1 and x of t2 are independent. So we start off with, over here, we autocorrelate it to E, expected value of x of t1 times the quantity x of t2 minus x of t1 plus x of t1. And we split them up into the expected value of x of t1 times the expected value of x of t2 minus x of t1 plus the expected value of x squared of t1. And, well, we know what this equals to. This equals to lambda t, right? Expected value of x of t is lambda t. So expected value of x of t1 is going to be lambda t1. Over here, we have expected value of x of t2 is lambda t2, etc., lambda t1. And over here, we found the expected value of x squared of t back in part A, where we can just show it as 1 plus lambda t1 times lambda t1. We distribute everything out, and we find out that for t greater than for t2 greater than t1, it equals to, or r of t1 t comma t2 equals to lambda times the quantity of t1 plus lambda t1 times t2. And then for t1 greater than t2, excuse me, this is for rt2 comma t1. Now this, what we're looking for is rt1 comma t2, it equals to lambda t2 plus lambda t1 t2, and you'll see the contrast between both. And that is homework number 10, problem number 1.